Yeah, it's really good to be with you this morning. I'm going to talk about instruction supporting students with developmental dyscalculia. What I want to say right at the outset is that I am not myself a teacher. I'm a researcher with a background in psychology and developmental cognitive neuroscience. So what I'm going to be talking about today is sort of reflections of what we know from research about what are some of the principles that should be used in order to support students with developmental dyscalculia. So just to give you an outline of what I intend to cover this morning, I'll want to first of all talk about the importance of developmental perspective, the importance of taking a developmental perspective and looking at foundational competencies, because I think that is really important when thinking about students who have math learning difficulties or any kind of academic difficulty that students might experience, is to try and understand where in their developmental trajectory may things have gone awry, and how can we backtrack, how can we go back to that, and how can we also generally just be cognizant and aware of the importance of taking a developmental perspective. And I hope to illustrate that with some examples. I'll talk a little bit about response to intervention and then review what we know about evidence-based approaches for the instruction of students with and also without math difficulties. Because I'll say right at the outset that I believe that there is no reason to suggest that effective principles for instruction should not apply to the entire population. That of course some students need to be given additional instruction in a tiered system, and I believe that's exactly what your conference is all about, this multi-tiered support system. But I believe that it's important to look at what works in general, and that will typically also work with students who have learning difficulties, although perhaps in higher dosages than those for students without that. So with that, I'd like to look a little bit more closely at what I mean by a developmental approach and why I think a developmental approach is really important. When we look at learning, we're really looking at the transition from novices to experts, right? When learners come into our classrooms, they're novices, and we're hoping to help them along this trajectory from novice to experts. So already within that, we can see a strong developmental lens. We know that knowledge develops gradually and that students need a lot of help in developing knowledge representations, and that they can then later on use those knowledge representations in complex problem solving and in more creative thinking about a particular academic domain. But the initial development of knowledge is quite gradual. And we go from sort of the formation of knowledge, if you like, to the application of that knowledge over developmental time. And a developmental approach also helps us to appreciate that there are differences between children in how they develop, in the pace of development, in the shape of development. And I think that can also help us to fine-tune instruction if we are aware of these individual differences in developmental trajectories. So I want to illustrate the importance of a developmental approach by showing how it can influence our choice of materials. So a lot of people in mathematics talk about the importance of doing real-world math. I don't know if you've been maybe following across the pond in the UK. The opposition party is advocating that, you know, if they get into power, they're going to do real-world math. And I was recently asked what I think about this, and it made me think about this particular study, and there's many examples like it. That is actually quite old now, but you know, the age of a study doesn't necessarily mean that, just like with wine, that it's necessarily bad. It could, you know, it could be quite good as well. So this is called similarity and numerical equivalence appearance counts, and this is a very, very simple task with very young children. It's a numerical matching task. And what children have to do is they see on the very top of the display, they see the sample, and then they have to decide which of the two displays at the bottom matches it in terms of number. And you can see some very subtle variations in the materials used. So in one, you've got dots to dots. Then in the next one, you've got shells to dots. And then you've got sort of a heterogeneous array of objects that children are matching to the dots. Now the question is, are there any age-related changes in how well children do on these three different tasks that all involve numerical matching? And you may say that, that the one furthest to the right is perhaps the most real world, or the one that is perhaps most fun. Well, it turns out that when you look at children from the ages of 2.5 to about 4.5, you can immediately see that there's one condition in which they are really quite good from the beginning, and that's the this to dots. So that's when you're essentially matching two things that look the same. However, as soon as you get to shells to dots, you see that it is only that there are differences even at age 3 and 3.5. So 3.5-year-olds, in other words, find it more difficult to match shells to dots than they find it to match this to dots. And all children find it even more difficult when you've got random objects and you're matching them to dots. So this, for me, really beautifully illustrates the importance of taking a developmental perspective and thinking very carefully at which stage of development can one introduce certain materials. In this case, it is only the appearance of the materials, but you can already see how very young children get distracted by the arrays away from quantity, and that makes it more difficult for them to do the matching, because the cognitive process that is required of children in this task is equivalent across the three conditions. The only thing that differs is the appearance of the arrays, right? So this is also to say that we need to be careful with slogans such as real world or engaging or fun when we think about instructional principles, because sometimes what we think is fun is actually distracting for children and making it more difficult for them to attend to the information that we are trying to convey. So I think that's a very simple but I think powerful example of how taking a developmental perspective in everything, including the choice of our materials, is really important. When we think developmentally, and this runs throughout mathematics, we have to appreciate that children learn differently at different points in development, and that very young children need concrete materials. They actually need to be able to feel and touch the objects that are going to become objects in physical space, are going to become objects in their minds. And this process means that they initially need to interact with them in physical ways as concrete materials, then move on to representations such as patterns on a page, and then eventually arrive at the abstract level of representations, which in mathematics would be learning numerical symbols and being able to understand the meaning of numerical symbols and engage in mental operations with numerical symbols such as mental arithmetic. And this CRA, which is also, this joke doesn't work in the United States, in Canada works so beautiful because it's the Canada Revenue Agency, which is the same as the IRS. But it doesn't, yeah. Thank you for the polite laughs. But the CRA, the concrete representation abstract continuum, is a beautiful example of how important it is to take a developmental approach and to always think about what are students ready to learn and how can I match what my materials are to what they're ready to learn. I think we also need to appreciate that there is great variability in developmental trajectories when thinking about instructional principles. And one of the domains I want to illustrate this to you with is mental arithmetic. And when we look at mental arithmetic, and I showed this, if anybody was in my first presentation, I showed this slide already, but I'm going to make the story a little bit more difficult. I wasn't able to quite elaborate in detail on it during that session. But when we think about the development of mental arithmetic, we know that students use different strategies and that increasingly they become more and more sophisticated in their use of strategies, right? So we know that very young children in kindergarten and in grade 1 will use their fingers, and they will use their fingers in a way that is quite effortful. So if they're asked to solve 5 plus 3, they might go 1, 2, 3, 4, 5. and then 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8. That takes a long time. At some point, the light bulbs go off and they're like, oh, I can just hold up 5 and just add 3. And that's like a cognitive leap, right? That's a new way of doing it. It's a new way of chunking knowledge, of breaking knowledge down into multiple parts. And so students go through this trajectory from counting based to eventually being able to retrieve the solutions to problems from memory or decompose them. Now, this looks very linear, as though every student goes through the same trajectory, right? But it turns out that if you look really carefully, that students are actually doing something that looks more like this, where students at different points in development will use multiple strategies at the same time and will use them interchangeably, right? And eventually they will arrive at a point where they're predominantly using retrieval, but even when they're using retrieval, they're also using other strategies. So this is another example of how important it is to think developmentally and not just to class a certain type of strategies immature and others as more mature, but to understand that students are very flexible, can be very flexible in their strategy use and will adapt their strategy use to the problem in front of them. And that means that even older students and even adults will at some points use their fingers to count. But it depends on the sophistication of that strategy. So development is always really important to take into account and to also understand that transitions in development are not binary. It's not as though you move from count-based to retrieval-based, but that even when you're in the retrieval-based space developmentally, you're still going to use counting strategies in some instances as well. This, by the way, I should credit is work by Bob Siegler, who's at Columbia, previously at Carnegie Mellon University, and this is work that they did in the 80s, so it's relatively old work, but very powerful work. And the only way that they got at this picture, which they got from this kind of linear story to this story of developmental complexities by testing children repeatedly over a period of 3 to 4 months to really capture how variable students are in their strategies. So development is incredibly important when thinking about instruction. I think a developmental account also helps us to overcome false dichotomies that exist. And I know that Corey Peltier is talking, I think, next door about exactly this. So maybe there's some overlap between our presentations. But I think if we think about the math wars that we've been having all across the world, right? And where we really get into this, into these stereotypical characterizations that, you know, you've got discovery math on the one hand, where everybody just wants to teach students conceptual understanding, and then you've got back to basics on the other hand, which is all they want to do is drill and kill math facts and only teach students one strategy. Well, if we take a developmental perspective, we know that these two things are not living in difference, that these are not mutually exclusive, but rather that in the mind of a developing child, in order for them to become better at mathematics, they need both procedural knowledge and conceptual knowledge. They need, that they need their math facts, but they also need to understand how addition and subtraction are related, and so forth. And so in this paper by Bethany Riddle Johnson and colleagues, what they found was that when you look longitudinally, you see that you can't really separate these different ways of knowing about math, but rather that they are iterative and form each other over the course of learning and development. So developmental perspective is incredibly important. And if we think developmentally, this is apologies for the typo, then we have to identify building blocks, and those can become the targets for screening and intervention. So I want to spend some time before I go into the review of what we know about the best instructional principles for children with learning difficulties in math, such as developmental dyscalculia. I want to spend some time reviewing for you what we know about some of the building blocks. So what do we know about some of the early developmental origins of numerical and mathematical abilities? Because we know that if we can go in developmentally, if we can target those early, then we can set children on a different developmental trajectory. So in my lab, as well as in many different research groups around the world, we've been asking the question, what are the early foundations of math? In other words, what are some of the components that are scaffolding mathematical learning in early development? If we think about, a scaffold like this, we do know that if the bottom parts of it aren't well built, that it's going to be shaky and potentially eventually collapse. The same with the foundations in the buildings that we live in. Those need to be solid, and we can think about development of academic skills in a similar way, that if we get the foundations wrong, then we can't assume that the rest of the building is going to hold up over time and weather the storms that we will encounter through its lifetimes. And a powerful analogy that I'm sure all of you in this room are very familiar with is that of phonological awareness. We know that children's awareness that language decomposes into units of sounds, which we can assess with things such as asking them to tell us whether two words rhyme or not, which requires them to attend to the sounds that make up spoken language. We know that their phonological awareness is predictive of their later reading achievement, and we also know that their ability to then connect those speech sounds with letters in the process of decoding or phonics, that is an incredibly powerful predictor of later skills. So in some ways, in the domain of mathematics, we're looking for the phonological awareness equivalent or equivalence in the domain of mathematics. And we think this is incredibly important, again, because if we take a developmental perspective, we know that children who lack foundational skills early on continue to lag behind their peers who have solid foundational skills. So children with good foundational skills enjoy a trajectory of growth in reading, whilst children without foundational skills do not. So we need to understand what goes on in terms of what are the key foundational skills so that we can screen for them and intervene early. So what do we know about the foundational skills underlying math? Well, a lot of research has been devoted to understanding how we process sets in the world around us. And this is sometimes referred to as non-symbolic number processing. Why is it called non-symbolic number processing? Well, because the notion is that you can look at this slide of dots and quickly judge whether it's smaller or larger than another slide of dots without having any knowledge of number words or Arabic numerals. And indeed, it turns out that even very young babies are able to discriminate between dot arrays. So you can present a 6-month-old baby as Fei Xu and Liz Spelke did back in 2000, with repeated displays of 16 dots, and you measure how long they look at those dots. At some point, babies get bored, rather quickly actually, but then you introduce a new slide of dots that's now 8 dots, and it turns out that 6-month-old babies notice that change. They become interested. Something new has occurred. And so they detect the change in the number of items in the display. Yet, at the same time, 6-month-old babies are not capable of discriminating between 8 and 12 dots. So it seems that they have a very fuzzy sense of numerical quantity, and that they can really only apply that if the differences between quantities are very large. But nevertheless, it suggests that perhaps we're born with some rudimentary intuitions about numerical quantity and numerical relations as well. And it turns out that if we look in other species, including in non-human primates, we find that they are quite capable of doing these number discrimination tasks. So rhesus macaques, for example, can learn on a touch screen to first press the smaller of 2 dot arrays and then the larger of 2 dot arrays. And no, they're not doing this for free. They're giving little fruit pellets or squirts of juice every time they do this. So this is work for them. But nevertheless, they demonstrate in laboratory settings as well as in the wild. There's some beautiful work doing observational work with animals in the wild. And everywhere you look, animals are displaying some rudimentary intuitions around quantities that they they use adaptively in their behavior. So one famous experiment showed that tigers are actually able to tell which is the larger group of approaching predators just by the number of calls. So in other words, there seems to be some evolutionary basis for basic intuitions around number. And we also know from lots of beautiful neuroscience work that there is a circuit of brain areas that involves chiefly the interparietal sulcus, highlighted here in yellow, that is involved in our ability to discriminate between quantities and is activated when we do these kind of non-symbolic discrimination tasks. However, when we think about human children, it gets a little bit more complicated, doesn't it? Because we're not just roaming around in fields and using numerical information to discover our food sources, but we use sophisticated cultural systems of representation for number, such as numerical symbols. And these have only been around for about 6,000 to 7,000 years. So these are relatively recent inventions, and we're not born with some brain area that represents numerical symbols, just like we're not born with a brain that is capable of reading. But instead, we have to painstakingly, during informal and formal education, learn the meaning of these, what are initially squiggly lines on a page. And same with the number words, that are essentially meaningless to a young child. And so this is a process of development, again, that we need to take into account. Yes, we may have those non-symbolic foundations that we share with other species, but numerical symbols are something that we need to learn. And indeed, a growing body of research shows that children's early understanding of numerical symbols is a critical scaffold for their mathematical development, more generally speaking. And I want to illustrate this to you by reviewing what I think is a really elegant study by David Purpura, Barudi, and Lonergan, called The Transition from Informal to Formal Mathematical Knowledge, Mediation by Numeral Knowledge. And what David and his colleagues did here was to conduct a longitudinal study. So children were first tested in kindergarten on what is referred to as their informal knowledge. So these are things like being able to count, being able to compare sets, being able to give the answers to simple story problems. And then later on in grades 1 and 2, they were assessed on their formal knowledge using calculation abilities as well as David Geary's number combinations test. So these formal assessments are more closely related to what they learn in elementary school, and the informal is more what they learn in kindergarten and in preschool more generally. And what you can see, and this is not very surprising, is that there's a really strong relationship between the informal knowledge and the formal knowledge. It's a correlation of 0.84, where correlations range from 0 to 1. So, it's a really great effect. But what was even more interesting was that David and his colleagues asked, well, what's the role of symbol learning in this developmental trajectory? And what they found was that when you included numeral knowledge, which was indicated by two tasks, one in which children simply had to say, what is this number? What's it called? So number naming, as well as set to numeral, where they saw a numeral and then had to identify which of these four sets matches that numeral in terms of quantity. Well, once you included that as what is called a mediator in the statistical model, it fully mediated the relationship between informal and formal knowledge, which means essentially that children who have good numeral knowledge early on are better able to make the transition from informal to formal mathematical thinking. So having symbols as a developmental tool to give you access to the ability to do problem solving and to be able to represent quantities is incredibly important. So when we think about number symbols, we all woke up this morning, and probably one of the first things certainly I did was to look at my smartphone and to see what the time was, and not to get into panic. Oh my God, I'm going to miss my first presentation. So I used numerical information to inform my decision making. Then I might have looked at the news and I would have processed lots of numbers, weather and so forth, and we do that really effortlessly, right? Because it's so ingrained in our brains. It is like it's second nature to process numerical symbols. But in the mind of a 4-year-old, this may just look like a squiggly line on a page. And then they have to learn that this numerical symbol refers to all sets of a quantity of 5. the symbol-quantity relationship, sometimes what we call cardinality. They also have to learn that the symbol is part of an ordered sequence and therefore carries positional rank information. And we know from research that children sometimes have great difficulties integrating these two concepts with one another, for example. They also have to learn, just like in reading, that this 5 is part of a visual category, and therefore, regardless of how badly you write it, regardless of what font size, what font type you use, it is still referring to the same underlying construct. And we now know that there are actually areas of the brain in higher level visual areas that are very sensitive to numerical symbols, sometimes called the visual number form area. So over the course of learning and development, our brains essentially develop specialized representation for the visual appearance of numerical symbols. And then children also have to learn that they can translate between different symbolic representations. So between the 5, as it is the Arabic numeral, or the written number word 5, or the spoken number word 5. And making these connections between these different ways of expressing numerical symbols is incredibly important. And then, of course, when we get to multi-digit numbers processing, everything becomes even more complicated, because now children have to understand that that there's a relationship between the position of the number in a multi-digit number sequence and its value, right? And we know a lot of children struggle with understanding place value. So numerical symbol learning is incredibly complex. And one of the things we know when it comes to symbol learning is that children vary greatly in what they know when they enter kindergarten or when they enter any kind of preschool program. So you're going to get some children who have grown up in houses where the parents are super keen and they've got lots of number books and they do lots of number activities. Then you've got other children whose parents are working 3 jobs and barely have time to put food on the table and are not going to be able to provide them with a lot of informal input. So you're going to have a lot of variation of children coming into classrooms. And therefore, it is really important to assess what they know to be able to inform individualized instruction, to avoid boring those children who are very far ahead and ensure that those children who are lagging behind or who haven't had the opportunities yet to acquire certain foundational competencies have the opportunity to acquire them. So in that context, it is really important to distinguish between knowing how to count versus knowing what counting means. This is in the preschool context. So this is what's referred to as cardinality. So cardinality is essentially the knowledge that I have that if I count these 4 chairs, 1, 2, 3, 4, 5, I mustn't mess this up, that there are 5 chairs in the first row here on this side. And so the last word in the count sequence represents the total number of items in the set. So how do we go about knowing whether a child understands cardinality? Because a lot of young children are really good at counting, and they're really good at sort of the sing-song of counting, and they really enjoy that. But yet, if you ask them after you've climbed a flight of stairs with them, let's say it's 5 stairs, you ask them, so how many have we just climbed? The child might not know them, yet we're perfectly able to recite the count sequence. That's the difference between knowing how to count versus knowing what counting is actually for. So how can we assess cardinality? So I want to show you a little video. I hope it works. But in this video, you're going to see my then 2.5-year-old son, Leo, and my former graduate student, Mariah Sokolowski. And this is a very sort of, not very sophisticated video. But what I want to show you here is what's called the give a number task, which is a really great way of understanding whether children actually know what the meaning of counting is or whether they're just able to recite a sing-song. So what Mariah's going to do is she's holding a puppet in her hand. You see that little dinosaur, the little blue dinosaur, yeah? She's going to introduce Leo to Dino and say that Dino, for whatever reasons, likes to eat blocks, likes to eat these green blocks there. And then she's going to say, can you give Dino X number of blocks? And then we'll see what happens, okay? And then we can discuss that afterwards. No, it doesn't work. No, it does. Oh, you can't hear. That's a kind of a problem. So what she's saying right now is could you feed Dino 1 block? So he was able to give her 1 block. Three blocks she's asking for now. And Leo gives 2 blocks. And she asked, is that 3 blocks? And he said, yeah. Now she's asking for 2 blocks. Okay, so hopefully what you could take away from this is that at this point in his development, Leo understood the meaning of 1 and 2, but above that, nothing, right? If he was asked for 3, he would perseverate at giving 2. And this is something that you will very commonly see with young children, that it takes them a lot of time to grasp the meaning of count words. And children essentially go through different knower levels. This has been documented in research. Between the ages of 2 and 5, they start out being 1 knowers, then they go on to being 2 knowers, 3 knowers, 4 knowers, and eventually they become what is referred to as cardinality principle knowers. Or they then understand really that the purpose of counting is to enumerate sets, and this does not emerge spontaneously. So I would advocate very strongly that in kindergarten, preschool context, something like a give a number test should be introduced as a test that can help educators to understand which students lack these foundational competencies. Because we know that cardinality matters greatly. This is work from University of Missouri by David Geary and colleagues who've done longitudinal work, tracking children over time. And what they found is that cardinality really matters. They conclude that the key implication is that it is not simply knowledge of cardinal value, but the age of acquisition of this principle that is central to later mathematical development and school readiness. So the earlier we can get children to understand cardinality, the sooner we unlock mathematics for them. Because without understanding the correspondence between the language of number or the visualization of number in its symbolic form and the quantities that it refers to, if children can't make that link, can't make that connection, then you can do whatever you want. They're not going to be able to learn mathematics. So that's really important. Cardinality is really important. And children, this has been shown, that children first learn about cardinality for number words and then later for Arabic numerals. So then we can ask the question, well, how do we assess children's understanding of Arabic numerals? And what researchers around the world have been doing is been giving people tasks such as this, a symbolic number comparison task, in which you're asked to judge which of 2 numerical symbols is larger. And this is a beautiful task because it allows you to assess how fluent is our children's understanding of numbers. So how quickly can they take these 2 symbols, translate them to the quantities that they represent, and then make a determination of which is numerically larger. And we can do this, of course, with symbols as well as with non-symbolic quantities such as $. And some years ago now, my then graduate student Nadia Nosworthy and I designed a simple paper and pencil test to assess this that we call the numeracy screener. It's available for free online if you want to take a look at it. It's a very quick test, 1 minute per condition, and we simply ask children to cross out the larger of 2 dot arrays or the larger of 2 numbers as quickly and as accurately as they can. This is the website in case you want to check it out. We're in the process of developing a digital version which should be ready in 2024. But we've been asking the question whether this 2-minute paper and pencil test, as measured in kindergarten, sorry?
Can you go back while we
Yes.
went really quickly? Okay, thank you.
Any other slides? That's good? Okay. And I will share these slides as well with the organizers so that they can be put on the website so that if you want to review them, you're most welcome to. So we've been wondering whether this 2-minute paper and pencil test, whether it predicts anything over developmental time. So when you're in kindergarten, does it predict, for example, your grades in grade 1? And we had the opportunity in collaboration with a number of school boards in Ontario to run studies, and this is work by Zach Hawes, who's a graduate student in the lab, who's now at the University of Toronto. But Zach showed that yes, the answer is yes. If you give children this numeracy screener in kindergarten, and then you assess their math grades in grade 1, you see a significant relationship whereby those children who did better on the numeracy screener in kindergarten then end up having higher grades in grade 1. And math grades, of course, are somewhat of a subjective measure of mathematical achievement, so these correlations are even higher when you use more formalized measures. And interestingly, what Zach also found was that it is the symbolic version of the test that really counts. So if you look in what's called a multiple regression, you don't need to worry too much about the numbers here unless you really love statistics. But this is essentially a test where you say, okay, I want to predict math grades, but I don't just want to use the numeracy screener. I want to use things such as their arithmetic, some measures of language, their age, their gender. And then I want to see which one of these variables is actually the strongest predictor of math grades. And we found that it's the symbolic version of the task. So again, pointing to the importance of number symbols and being able to process number symbols fluently for later achievement. I also mentioned ordinal processing early on, and I want to really highlight that there's a distinction between children's understanding of cardinality and their understanding of ordinality. Those two things are obviously related, but as you will see, they are slightly different from one another. So Arabic numerals are obviously part of an ordered sequence and therefore carry positional and rank information. And one of the ways in which we and others have assessed children's understanding of ordinality is by giving them what we refer to as a triplet verification task. So you see 3 numbers and you have to judge whether they are in numerical order or not. So 1, 3, 5, you would say yes. 3, 1, 5, obviously you would say they're not in numerical order. And in this study by Ian Lyons, who's now an associate professor at Georgetown University, we looked in a relatively large sample. I think it was 1,300 children between grades 1 and 6. These were children from the Netherlands. We looked at various predictors of their school achievement and their performance on standardized tests of math. And one of the things I want to show you here is sort of the interesting developmental dynamics, again, going back to the overall point that development is really important, between cardinality and ordinality. So this is our cardinality task where we ask which one is larger. You need to be able to link symbols to quantities. And this is our ordinality task where we now ask them to judge, is this number sequence of 3 in order or not? And when we look at how those two tasks relate to mathematics achievement over the grades 1 to 6, we see this really interesting trend whereby this is just showing you on the horizontal axis the grades, grade 1 through to grade 6, and then on the vertical axis is just showing you how strong is the relationship in this case between number comparison and math performance across grades. And we can see that early on, number comparison really matters, but then its predictive power declines. When we then look at ordinality, oh no, it's for some reason I'm missing that slide. I apologize. You're gonna have to trust me on this, and I'm gonna put that slide into the deck when I submit the presentation. But when we look at ordinality now, what we would see is that it starts out around 0, and by grade 6 is the strongest predictor. So there's almost this intersecting pattern of ordinality and cardinality over development. And we think this has to do with the fact that children change in the way that they process numerical symbols. Initially, they're very much tied to the concrete representations and to the quantities, and eventually children are able to make inferences about symbols simply by their position in the number sequence and their relationship to other symbols within that number sequence. So it's a sort of more sophisticated symbolic thinking that gradually emerges over the course of learning and development. Now, we are in a session that's all about instruction, so the question is then, how can symbolic number knowledge be strengthened, especially in the early grades? Well, one of the really interesting findings is that something as simple as playing board games, and very specific linear board games, such as snakes and ladders, chutes and ladders, rockets and comets, these are all different versions of the same game. You probably are all familiar with this game. You have a dice and you throw it and you move along this number path. And then when you encounter one of these snakes, you have to slip down, and it's very annoying. When you have a ladder, you're close to winning, but then if you get that ladder to 99, there's still a snake lurking there. No, actually there isn't for 99. But if you go to 90, you still have to, pass these obstacles. It's actually incredibly fun, and 4 to 5 to 6-year-olds really love this game. It's cheap, and it's an incredibly powerful intervention because Gita Ramani and Bob Siegler have shown that you can get these quite stunning improvements through playing these linear board games. And why might that be? Not just because they're fun and engaging, that's the part that gets you to the knowledge, but because they teach children about cardinality, about ordinality, about place value, about all of these things that I've been talking about in a way that isn't like sit in a row and listen to me talk to you about this, but it's let's do this game together and we can abstract these principles and they will transfer. And what's really fascinating is they went really deep into this research to try and understand whether it is the linear nature of the number sequence, and it turns out it is. If you have sort of a circular number sequence, these kinds of games don't work as well. So it is about the linear understanding, also the relationship between number and space that I think is really important here. And then, of course, we can do lots of things in play-based settings in preschool. I'm just going to show you some pictures I've taken of classrooms or that I found by following different schools on social media. But this activity is really simple, but yet deeply sophisticated because it teaches children to match symbolic and non-symbolic representations of quantity. And if you look carefully at the dot arrays, it also teaches children about the invariance of sets. What I mean by that is that if we look at this beautiful set here, what we can see is that they all contain the same number, but they're in different spatial arrangements. And that's really important for children to learn, right? That the set does not vary regardless of how it is spatially organized. It's quite an abstract thing to grasp, that there is sort of an invariance of number that supersedes differences in physical appearance. Then these beautiful learning carpets. This one, I think, shows you very nicely how to instruct children on making the link between symbolic and non-symbolic representation, but it also tells children about invariance, right? Because these numbers are printed in different font sizes. And look at what I find really nice about this is that the children are doing some reversals. The 5 is reversed, and children reverse their letters. They also reverse their numbers, and this is, by the way, a completely natural process of human development. Because symbols are one of the only objects in our environment that aren't mirror invariant. If I have a cow, I can flip the cow, it's still the same cow. If I have a 5 and I flip it, it becomes a different representation. So our visual system needs to adapt to that. And then, of course, you can be extremely creative with this kind of activity. And this is where we now get into the realm of spatial representations as well, which are so important for early math. There's such a tight link between number and space. And I'll talk a little bit about that towards the end of my presentation to elaborate on that a little bit more. But there's a lot we can do in the early years. This is something that me and my son did because he saw me preparing a presentation, and he saw this image, and at the time I think he was 5, and he said, "Papa, I want to do that." So we grasped everything that we could and recreated this on our living room floor. This is just to say you don't need sophisticated materials to come up with these kinds of activities to strengthen children's understanding of number. You can take everyday objects, you can take whatever you have lying around, and don't ask me what that stray ancient phone is doing up there. I have no idea where that came from. This gives away my age. Many young people wouldn't even know what that is. There's also really good empirical research to show that you can improve preschoolers' basic arithmetic skills through training them on with number magnitudes, especially with symbolic magnitudes. So this is work in which they used activities such as this, where you have to now match the teddies to the magnitude that is represented on these sacks. And so you would put the largest teddy to the 7, smallest to the 1, and the middle one to the 4, obviously. And of course, there's nothing about the symbols that gives away the quantity, neither is there about the dots. And these kinds of training activities, and also activities that involve number lines, we'll talk more about number lines towards the end of the presentation as well. In this case, you would place the 12 somewhere on the continuum between 1 and 20 and give some kind of feedback. It turns out that if you do this kind of training, what you find is the following. So let me take you through this. On the horizontal axis, T1 is the first time children were tested prior to the training. T2 is immediately after the training. What you can see is that in the control group who didn't receive that training, that's the flat line, they don't show any improvement. The group that shows the largest improvement is the group that worked with the symbolic task. So worked with the number line symbols, worked with the symbolic version of this task, right? They show the largest improvement in terms of their arithmetic performance versus those children in either the control group or in the non-symbolic group. So really strong evidence to suggest that symbols are really important, and we can do things in instruction for children with and without mathematical learning difficulties to strengthen their symbolic system, their symbolic understanding from an early age onwards. How much time do I have? 15? Okay, excellent, that's perfect. That's great. So I want to switch gears a little bit now, though it's very related, and look at evidence-based intervention. What do we actually know? What do we not know? Because there's always a lot that we don't know, right? We have to be honest about that. Although research can fill a lot of gaps, there's a lot of things that research has not addressed, and I want to also highlight those. So what I'm going to do is I'm going to review for you briefly within the next 15 minutes some of the recent systematic reviews that have been published in this space, as well as syntheses that have been put together specifically to inform educators. And then I want to also ask whether spatial training is effective, and I don't think I'll get to why minimal guidance is not enough, but we can talk about why minimal guidance is not enough, which would actually lead us back to the whole emphasis on development. But let's look at some systematic reviews. This was published, I think, just 2 years ago, and therefore I think is one of the most up-to-date reviews of what we know about interventions to improve mathematical achievement in primary school-age children. This was done out of the UK, but the review, as you will see later, includes studies from across the world. They really try to be inclusive. They reviewed a total of 45 randomized controlled trials that fit their inclusion criterion. They also looked at 35 quasi-experimental studies, and I think this is really important, because sometimes we think that randomized controlled trials, anything that isn't a randomized controlled trial, is not valuable evidence. But we can also gain insights from smaller scale studies, from less controlled studies, right? Educational settings are there's a lot of noise within them, so we can't completely control for that. These studies were conducted between the years of 2000 and 2017, and they only included students who did not meet the criteria for math learning difficulties. So I thought to myself, should I include this study in this presentation, because the presentation was pitching more towards helping students instruction with developmental dyscalculia. But as I said in the beginning of my talk, I really believe that what we can learn from good, high quality instruction at tier 1 informs everything else, right? And that the instructional principles do not differ in sort of major qualitative ways. So the studies were predominantly from North America and Europe, but there are some studies from the Middle East, Asia, and one solitary study from Africa as well. So they try to be as inclusive as possible. So what they found after reviewing all of this evidence, and I don't know if you know what goes into this, but it's a rather painstaking process where you essentially have to screen hundreds and thousands of studies to select those studies that meet your selection criterion. That's why it's called a systematic review. What they concluded from this review was that there are 7 points that are really important when considering instruction in early mathematics. The first one is focusing on key topic areas in mathematics, such as conceptual understanding, magnitudes, and basic number skills. The second one is ensuring that children have a fluent grasp of mathematical facts. It doesn't mean that those mathematical facts only need to go into their minds and their brains through some drilling procedure. There's multiple pathways towards mathematical fluency. Ensuring that children have a wide bank of strategies to complete mathematical problems and that they know when best to apply them. I think this is a really critical point. It's not just about knowing multiple strategies, but it's about being adaptive in a situation. We do it all the time, right? Sometimes I know oh God, I don't know that fact anymore, but how can I quickly get to the solution? The appropriate use of objects as a learning aid, that's going back to what we discussed in the beginning with regards to the CRA, the concrete representational abstract continuum, providing effective and timely feedback, and using technology that has been developed with a clear understanding of how children learn. And finally, varying how mathematical content is delivered in the classroom, such as through physical activity or group work. So variations in the delivery to keep things more engaging. In terms of policymakers, their recommendations are that the development of guidance on intervention should be made with caution, as the majority of the evidence that we've identified was of low quality. And there we go with what do we not know, right? There's a lot of research out there, but not all of it is good, right? Just because it's got research on as a label and it's published in a journal article, it doesn't mean that it is of high informative quality. Support teachers through training on evidence-based education so that they can evaluate studies that may help inform their practice. I think this is really, really important, is to provide educators with literacy around how to evaluate evidence that is in front of them. I just briefly want to diverge here and talk about where I think an example of where this went really wrong in recent years. I don't know if any of you were sort of practicing when there was a wave of enthusiasm about training working memory. Anybody remember those days? Yeah? And there was a whole industry of products that were being sold to boards and districts around training of working memory. Turns out that none of them did what was on the box. They made people better at the specific working memory task, but they didn't make children better at using working memory and applying it in contexts such as mathematics. And then finally, develop a core outcome set, an agreed set of appropriate outcome measures to aid comparison across studies. But what I want to turn to now is that systematic review is helpful, but I think what is even more helpful if you've got students struggling with mathematics in your classroom is this recently published Educators Practice Guide from the IES that was put together by Lynn Fuchs and many other researchers in the United States that are really world leading when it comes to understanding mathematical learning difficulties and instructional principles around them. And I highly recommend downloading this guide. It's free. It contains a lot of information. I'm just going to give you a high-level overview of some of the key recommendations that they put out. And these are 6 key recommendations for which they say they have strong evidence, and they provide you in the report with the evidence. So it's not, you don't have to take their word from it. You can trace the articles back. The first one being to use systematic instruction, to provide systematic instruction during interventions to develop students' understanding of mathematical ideas. So here's one of those examples. If you want to teach children 4 times 6, they might offer you a solution where you have 4 groups of 6 items. Well, then you can systematically draw their attention to that. Another strategy is to have 6 groups of 4 rather than 4 groups of 6. And as you can see from this guide, there's lots of information in this guide how to concretely implement these 6 principles. The second one is mathematical language. And here, what they say is, really use the mathematical language to describe the concepts that you're trying to teach, rather than some shortcut words that don't really generalize and don't really help students develop a deep understanding of those mathematical concepts. So for example, when you've got a unit fraction, you say a unit fraction is when the numerator is 1 and the denominator represents the number of equal-sized parts of the whole. And then you compare that mathematical language with these graphical representations, right? Which is also really important, is to use these multiple representations and to show children how they refer to the same central underlying conceptual knowledge. Representations, this is where we get back to the CRA, not to the Canada Revenue Agency, but to concrete representational abstract, where you're trying to solve a problem such as 5 plus 4, and there's many different ways of doing this, with concrete, with semi-concrete, representational kind of things. And there's multiple ways, of course, of doing this, by separating the 2 operands into different piles or into different representations on a page, or by putting them together and counting them up. So there's lots of really good information in this report. They strongly recommend the use of number lines. I think this is really something that has exploded in the last 15 years, is the use of these spatial representations to illustrate concepts. And one of the things that is really beautiful here, if you look at this number line, how much information is in there? It's about positive, about negative integers. It's about whole numbers. It's about fractions. And they're all represented within the same spatial continua. And that can really help students. And Bob Siegler has come up with this theory, this integrated number theory, where he argues that the spatial representation of quantity can really help students to understand how fractions are also magnitudes, just like whole numbers, right? Which is an understanding that students often lack. So these number lines can be really effective. Word problems provide deliberate instruction on word problems to deepen students' mathematical understanding and support their capacity to apply mathematical ideas. So they say that it's important to teach students to identify word problem types that include the same type of action or event, and expand students' ability to identify relevant information in word problems by presenting problem information differently. So they really recommend working on that, and that of course ties back to mathematical language. It also ties back to explicit instruction. So all of these things are kind of nested with one another. And then finally, and this is perhaps the most controversial one, I don't know why it's so controversial, but people write lots of articles about this, and it gets very heated discussion on social media, which is regularly include timed activities as one way to build fluency in mathematics. One way. The one way is really important here. So identify already learned topics for activities to support fluency and create a timeline. Ensure that students have an efficient strategies to use as they complete timed activities. Not just throw timed activities at students, but make sure they're at a level of mastery where you can now go from, yes, there's conceptual understanding, let's now make that fluent. Let's build those neuronal pathways so that you retain that knowledge. So I think that's very good. I don't do full service to this report because it's, I think, way over 100 pages long, but it contains more concrete advice than I've seen in most resources. So do take a look at it. Finally, I just want to briefly talk about something that I find really exciting, and something that I think in mathematics education we need to really pay a lot of attention to. Math is so closely related to space, so that this raises the question whether spatial training can transfer to math. And as I said, mathematics ability and spatial abilities are closely related. My former student Zach Horst did his PhD on this, and one thing that we did was we took all of the brain imaging studies that had looked at symbolic number processing and mental arithmetic, and all of them that had looked at mental rotation. So mental rotation is in blue, mental arithmetic is in green, and symbolic is in red. The take-home message is if you look at the parietal cortex, I know I'm not supposed to, the cameraman is looking at me, but if we look at, I'm just kidding, if we look at Z equals 43, sort of in the middle, there's a lot of overlap between these colors, right? And that's in the parietal cortex. This part of the brain seems to be doing spatial transformation, numerical knowledge, and mental arithmetic at the same time. So we think there's something very inherently spatial about math. So the question then is, can spatial training actually improve mathematical skills? And Zach, following his PhD, addressed this question in a meta-analysis. So that's where you take all the available, lots of people have tried spatial training. Some have reported good evidence, some have not. You need to take them all together and look at, on average, what does it look like? And the way it looks like is here. Again, very busy graph. Don't worry too much about the detail, but if I could just convince you to look at the dotted line, that's 0. That means there's no effect of spatial training. Then all of these lines are individual studies, and then the beautiful diamond at the bottom is what is called the meta-analytic estimate. So on average, if we take all the evidence together, what do we find? Is there a there, or is there nothing? And as you can see, it is to the right of 0, which means there's positive evidence, right? So spatial training does seem to improve mathematical abilities. Interestingly, they also found that this effect is greatest for the oldest children. So spatial training later on, perhaps because the concepts are different and the concepts are more spatial in nature, it seems to help students there. They also found that spatial training Yeah, increases with age. And interestingly, it was stronger when using manipulatives versus computerized training. I think this is an important dimension to investigate, especially with young children, right? We're giving young children a lot of iPads and tablets, and EdTech is important and can be very, but we have to remember that it skips the concrete on the CRA, right? It goes straight to representation. So we still have a job to do with manipulatives. The mechanisms of these effects remain unclear. So, conclusion. Developmental perspective is crucial. If the only thing that you take away from my presentation today is to always think developmentally, then I'll be really, really happy. Building blocks of math, symbolic number knowledge is critical. It is malleable, so it's something we can do about it. It informs targets for intervention and helps us to identify starting points, and it also helps us to resolve false dichotomies that take up way too much airtime when we should be really thinking about students rather than do we think that this type of instruction. Well, we should be using all of these things intertwined with a developmental perspective. Evidence-based approaches are sparse, but principles of good interventions are clear. And the final thing I would say is that spatial training is promising. So, when you think about students in your classroom or in the context that you work in, think about, can we talk a little bit more about space and how can we integrate space into our math lessons, starting with the number lines, but there's also other ways of doing that. So with that, I'd like to thank you very much for your attention and be happy to take as many questions as we have time for. Thank you. Yes.
More about what spatial training looks like?
Yeah, so the question I was told to repeat the question. So your question is, what does spatial training look like? It can involve a number of things. It can involve, this slide I think shows it. It can involve working with things such as these kinds of shapes or doing actual mental rotation tasks, asking children to tell you, which of these two cars is in the same orientation. There's actually a really good book, and I have no financial interest in this. It's called Taking Shape, which describes a lot of spatial training activities for young children. And then, of course, using number lines as well is a form of spatial training, but then it's very close to the actual thing of doing the math.
How much time do you give a child before you determine that it's a developmental dyscalculia? Or
That's an excellent question. So the question is, how much time do you give a child before you determine that it's developmental dyscalculia versus a delay, right? I don't think we have an answer to that, but here's my attempt to answer your question. Never rely on one observation, never rely on one standardized test, but repeatedly observe children over time. Because a lot of the research, so years of investment went into early identification of developmental language disorders. And people thought they had these beautiful tests that would tell you, this child is going to end up having a developmental language disorder. Well, the more longitudinal work they did was they found that there were lots of false positives because children have such variable developmental trajectories, and especially in the early years, because our assessments in the early years are terrible too, right? Because they won't sit with us for half an hour and do our beautifully psychometrically validated tests. We will need to come up with simple solutions. So I would say look for stability of patterns, right? And look within your multi-tiered systems framework, look at how they're responding to intervention and how they're moving up and down the tiers, right? And how long they are. I think that's what I would say. And I would say that even a child that is diagnosed with dyscalculia formally still has the opportunity to learn math. That shouldn't be the end of their learning history in mathematics. But it will hopefully give them the right accommodation and the right recognition as they move throughout their lives that they have a difficulty, right? I don't think we're there yet as far as we are with dyslexia. With dyslexia, we've made so much great progress, and so great, but we need more progress in dyscalculia as well. Yes?
So I'm a parent. I have a 6-year-old who struggling greatly, the one-to-one correspondence, the representation, all of the things that you were talking about. I see that, he's still definitely 1, 2, 3, 4, 5. those types of things. We're about to do new psychological testing of him and do cognitive assessments. Are there certain types of tests, I mean, I know that you're in Canada, that I should be looking for, maybe in this room of the psychologists here, I should be asking about? Because when I asked our school psychologist, she didn't seem to know a lot about dyscalculia.
Yeah, that's very common.
Second point before you answer, so I see my 16-year-old who has very severe dyscalculia, and I see that, you know, all the tried interventions that we tried to do for Connor never worked. So as a parent, I'm like, okay, I want to do the right things for my 6-year-old. We're the beginning stages. We can still do some interventions and things like this. So just the long lens didn't help my 16-year-old. Trying to help my 6-year-old. What should I be doing? What should I be asking for?
So I have to summarize your question, so I won't be able to repeat it in full, but the gist of what I got was you're asking me, you have a 6-year-old who's struggling with fundamental concepts of number, how to help them, what kind of tests should be used to assess them, and then as a contrast, you have a 16-year-old who has great mathematical learning difficulties and you don't want to repeat the same mistakes. It's a very hard question. I'm going to do my best to answer it. At 6 years of age, I think it's very difficult to do anything that is really diagnostic. It's at the level of screening, right? So I would say that there are some tests around that you might be able to recommend to your school. I'm thinking about the number sense test from Nancy Jordan. I'm thinking about the Pfeiffer mathematics assessment that is out there, but I'm not an assessment specialist. So those are just two that I've heard as being strongly recommended. In general, I would try to find as many different ways to engage your son or your child, your 6-year-old child, in mathematical activities, and avoid creating a scenario whereby they become math avoidant, because you've essentially exposed their problem so much to them that now they're like, well, I'm not good at that, I might as well not do it, right? And that can then be this vicious cycle between math avoidance and math achievement and math anxiety. So those are some things that I would say. And I would, keep advocating, I think, for, especially because you have another child in your home who has these difficulties. So you know that it's real, because I think sometimes it's hard to convince people that it is actually real. So yeah, those are my thoughts. I'm sorry that I don't have like the decisive test or approach to solve that problem. And take a look as well as at this IES guide. I think it's useful to educators, but it's potentially also very useful to parents if you want to do some of these activities at home. Yeah.
I didn't see that your presentation was included. Will that be uploaded?
I am one of those people who tinkers with their presentation the night before. So I will most certainly submit that to Kelly, I believe, right? Yes. So that you will get the slides. And I will add that missing figure as well. At the back there, yes.
So I have a daughter that has dyslexia and dyscalculia. And, I also teach kindergarten. So and my kids are they're chronologically ready for kindergarten, but no exposure, anything like that. So, like you have said, dyslexia, there's a lot of research, like Orton Gilliam's like the guru of, is there anyone for math, like where I can follow these to get like specific like approaches and ideas?
I mean, there are a number of resources that I would recommend. The first one is always look at what IES is putting out. The other one is there is an approach out of Canada. It's a charity called Jump Math. Junior Undiscovered Math Prodigies is the it's a full curriculum. It's Common Core aligned. God, I'm trying to think what other places can I recommend. There is a group that is calling themselves the Science of Math that is trying to sort of do the same thing as the Science of Reading. I have my doubts whether we can really call it this, whether we can really draw the same equivalence, but some of their recommendations are really excellent. Also the work of Lynn Fuchs at Vanderbilt. She's the most highly cited educational researcher in the world. Her and her husband have developed intervention strategies for both reading and math throughout their careers. So they've got tons of great stuff there. So look at that as well.
Thank you.
How are we doing for time? Yeah? Okay. Well, thank you.